today we will be discussing the likelihood principle. The likelihood principle is a source of, I would say, rich argument in world statistics, and that a lot has been written about it. A lot of it, people don't agree on parts of it. So what we will be doing is that we will talk about what the likelihood principle is, what the source of contention is, and how it relates to data reduction, because this is still the chapter on data reduction. So, we'll see on next questions. Let's begin. So, we have some project actually. So there are some nice references on this, which I will be sharing with you. But for now, until we get a projector running, we'll just use the board as usual. So, what is the likelihood principle? The likelihood principle is stated as.
Sorry, can you please raise your voice?
Oh, no. Sure. Yeah. So, what is the likelihood principle? The likelihood principle in our main reference text, Salem and Berger, is stated as basically given given two data sets or data points, x and y. I'm using the vector notation here. What the likelihood principle says is that if the likelihood of some parameter in your model, theta, given that you observe the data set or the data point x, is proportional to the likelihood of theta under you observing data set y multiplied by some constant, it's a function of x and y. If you have this kind of proportional relationship, if you have this proportional relationship holding, then your inferences should be the same regarding whether or not you're using data set x or the data set y. So what is this saying? This is basically saying that your inferences should depend only on the likelihood, that the likelihood captures all that is important about the data. This is incredibly important. So suppose one thing I imagine you guys have done or will be doing pretty soon is likelihood ratio tests. A lot of you I know are taking linear models and experimental design, so we will be doing likelihood ratio tests. And as you can imagine, if this is a constant, so let's say I'm testing just a space, I'm just going to write this. I'm going to test a hypothesis of theta 1 versus theta 2 in my model. So if this is a constant, then this has to be just equivalent to any result that you get using instead your y data set, because the constants simply cancel out, is what this is saying. So again, let me just go a bit into the notation here. What does it mean that the constant is a function of x and y? It simply means that you can change your constant for every set of observed x and y. It really doesn't matter. All that matters is that your constant is independent of theta. Okay. Any questions? So, again, what we're saying is that inferences should give you the same result. In a setting kind of like the likelihood ratio, that is. So I'm going to give another example where I want to do inference using credible intervals. So let me pause for a second and see if we can access this projector again. Just a second. back to the likelihood principle. Going to relate this to the concept of data reduction, which we've been talking about these past couple of weeks. So suppose I want to do inference using credible intervals. What we were saying using the likelihood principle, that the data, or whatever inferences you can get from the data, you can get from just your likelihood function. The likelihood function basically encodes everything you need, is what this is saying. So a very nice example here that we can give is the what is known, sometimes called the fiducial distribution. Imagine, for example, a data set that is coming from a normal distribution where you know the variance, sigma squared is known, and you want to do inferences on the mean of this data set. Suppose you adopt the Bayesian approach or the fiducial approach, whatever you would like to call it there, computationally equivalent for this kind of problem. And we're going to do inference using credible intervals derived from the posterior distribution on theta, the mean of this normal distribution. So using a uniform prior over there gives me the nice form of just the likelihood. We're only dealing with the likelihood if I'm using the uniform prior. One thing that we need to note here is that the likelihood is not PDF, so you need to adjust for that. So when you have your likelihood and your uniform distribution, you see here like you have a proportional to likelihood sign. That means you have to have a constant in there to turn it into a PDF, which you can use for credible intervals. In this case, like some of you may be familiar with, the constant in this case would be the exponential of I bar 2c squared. This is the constant that we would multiply by the likelihood function here to make this a PDF. This is constant again, of course, because we're assuming that the data is fixed, that we observe the data. So what would happen here if you just appropriately multiply this constant is that your posterior distribution on theta is now normal distribution with mean x bar and variance sigma squared over n. And I can just, as you can see on the slides, I can just use my credible interval and make inferences about theta. So how do we relate this to the likelihood principle? In particular, we're going to relate this through the concept of sufficiency. So if the likelihood principle holds, the first one, you get the proportionality, which we were talking about over here. And then your ratios between the two likelihoods, given x and given y, are just constant. So in our example, I have the likelihood, and I said this is my constant. So let's see. So I have the likelihood of theta given x times this function. And if I want to divide this by the likelihood of theta given y, I'm going to move this over. I'm using y as an infinite distribution, and this will be this is your function as a function of the x and y that we were talking about. Notice that this is perpendicular to theta. I mean, it's independent of theta, orthogonal. So this should kind of remind you of the condition that we had earlier for minimal sufficiency. you recall that we did something kind of like that. We had constants that were orthogonal to theta. So it would seem that minimal sufficiency is somehow related to the, or sufficiency in general as a concept is related to the likelihood principle. So how is sufficiency related to the likelihood principle? So if your sufficient statistic, in this case it's the minimum sufficient statistic, if your sufficient statistic is the same under this same model assumption, then obviously you get the same credible intervals, which would lead to the same inferences. That might seem kind of like a trivial conclusion, certainly nothing to have an argument about. Well, the argument is not when you're in the case of the same model. So we assume here implicitly that both data sets, x and y, came from a normal distribution with the same parameter theta and the same parameter sigma squared. So this is not really a problem. This is pretty obvious. This is known as the weak likelihood principle. The source of argument, or the source of tension, is really the strong likelihood principle when these come from different models. So we're going to go into that, but before I jump into this, let me just do a quick rephrasing of my likelihood principle. So from James Berger, basically what he's saying in his book is that inferences again should depend only on the observed outcomes, what you observe, your x's and your y's from data sets, through their likelihoods. And one thing that we've all come into contact with that doesn't really do that is p-values. P-values do not depend only on your observed data. This might seem like a counterintuitive thing, certainly seems that way to me. What does it mean? So I'll give you an example of what I mean when I say that p-values do not depend only on the observed data. So suppose we have two different measurements of features, feature x and feature y. These two measurements both have the same parameter, theta, so theta is the same parameter in both sets. Maybe it's the mean, the variance. The important thing is that if it is the same, measuring the same thing, so to speak, or expressing the same thing. So you can see from these numbers, all of these satisfy the likelihood principle in that under different thetas, theta null and theta 1, the ratio of the likelihoods under x or under y is the same. It's pretty obvious for x equals 1, for y equals 1. Maybe less obvious for 2 and 3, but I guarantee you that they are the same. So the likelihood principle is satisfied everywhere. So according to the likelihood principle, you should make the same inferences, meaning you should make, or you should get the same conclusion about theta, regardless of which experiment or data set that you're getting. So let's see, if we're doing the likelihood ratio test, then let's say if x equals 1 or y equals 1, in both cases, you would prefer theta null over theta 1. The ratio of the likelihoods just tells me that theta null is more likely. Suppose you're testing using p-values. So one way you construct your acceptance for rejection regions, let's say if x equals 1, then you fail to reject theta null. Otherwise, you accept the alternate hypothesis of theta 1 under x. So what about y? So if y equals 1, then suppose you also decide to follow the same rule, the same rejection rule, that if y equals 1, then you're going to accept or fail to reject theta null, and otherwise you're going to accept theta 1. So you can pretty easily see the type 1 error rates for y are not very pleasant. if you do follow that rule, then you'll get a 0.74 type 1 error on your test. If you are rejecting whenever, if you are, rejecting whenever y is not equal to 1. So you can see the testing is very different. If you're using a likelihood ratio test, that's very different from what you would see if you're using simple p-values. And again, so someone might argue that this would be obvious when you look at type 2 errors, that the issue would be obvious here. But let's see a slightly more contrived example. So again, consider the rule where you fail to reject data null when x equals 1. This is once more equivalent to failing to reject theta null when y equals 1 if you're using a likelihood ratio test. We're following the likelihood ratio. For the likelihood principle, x equals 1 gives you the same information as y equals 1. Suppose instead you opt for a p-value test where you reject if x equals 1, fail to reject if x equals 1, and on the other hand, fail to reject when y equals 3. So clearly you would have no type 2 error for the second data set. Type 2 error is 0. So that seems desirable, and you only have a 5% type 1 error, so the test seems like there's nothing wrong with it. But you obviously want to include the situation where y equals 1 into like factoring what your inferences are. So you want or at least that's one way to look at it. If you observe y equals 1, then maybe actually you want to fail to reject that theta as theta null. So that's a very, very small difference of 0.001, and it leads to a change in your inferences. So I would say this is the gripe some people have when it comes to reconciling p-values and the likelihood principle. So earlier we said that the likelihood principle necessitates that your inferences only depend on the observed data through their likelihood. So why do I say that p-values do not depend on the observed data? So very simply, p-values, when you say if y equals 1, you're also taking into account the situations where y equals 0, 2, and 3. That is what we mean by it takes into account unobserved data from your model. So, moving on to a counterexample supposed counterexample for the likelihood principle. So again, likelihood principle says if I have proportional likelihoods, then I should be making the same inferences. But consider this binomial or negative binomial experiment. Suppose an individual runs an experiment where they flip 20 coins and they get 7 heads. Well, one thing that we need to model this is that what did the person have in mind while they were actually doing this experiment? Did they set the number of trials beforehand? Did they say we're going to flip 20 coins regardless and see how many heads we get? Or did they say, okay, I'm going to fix a number of heads that I would like to see and flip as many coins as I need to get the outcome that I need? So notice in both of these models, my theta here would be measuring the same thing, measuring the probability of getting heads. So the argument here is about the strong likelihood principle. These are two different models, and they're still working on the same theta. They're measuring the same thing. We're trying to get inferences on the same parameter via different models. I would like to run a simulation and show you how to run for this. So these are the likelihoods. So you have your binomial likelihood and you have your negative binomial likelihood. These are just proportional up to a constant. Same thing, pretty much. So you, by the likelihood principle, you should be getting the same inferences out of these. In fact, when you adjust this code just a little bit, they overlap and you will not be able to see the difference. So if I adjust for the constant, I'm doing once you adjust for the constant, it goes away in the likelihood ratio test. These things just overlap. So pretty okay so far. Now let's see if I use p-values with null hypothesis being that my probability of getting heads on a coin is 0.5 versus the alternate of it being less than 0.5. So we define the p-value for this problem as getting something that is more extreme. So more extreme in this case would be getting, in the binomial model, it would be getting 7 heads or less if in fact your probability was 0.5, and the number we get for this is around 0.13. So let's instead do the negative binomial model, where the more extreme probability is getting the same number of heads, 7 heads, in more than 20 or more trials, so to speak. So you get more than 13 failures, basically. And the probability is 0.08. So under these two different models, you get two different p-values. But the likelihood principle says you shouldn't. It says that if they're proportional, then you should be getting the same inferences. I mean, these are completely proportional to a constant, but we're getting different p-values. So again, this is an argument regarding the strong likelihood principle, which is discussing two different models. If they are from the same model, then it is trivial, you're going to get the same results. But so what do we do about that? What are some counter arguments for this example? So are we really getting different inferences? We are getting different p-values, but so one of them was 0.13, one of them was 0.08. So what's your cutoff? If your cutoff is 0.05, then you could just argue that, okay, you're going to get the same inferences regardless. If it's 0.1 or 10%, then you are going to get different inferences. But that again brings us back to the subjectivity of the threshold, or what does it mean to have a different inference? In the credible intervals example, this was pretty obvious, maybe not so for the hypothesis testing example. And so the second point that we need to consider for this argument is that the likelihood principle is not accounting for the poor choice of model. So the experiment where you decide to flip 20 coins and observe the number of heads is not the same experiment as where you decide to flip any number of coins until you get 7 heads. Those are two different things. And one of them involves a stalking rule. So generally anything that involves a stalking rule is going to mess with the likelihood principle. But the question is whether or not this kind of invalidates the likelihood principle or its implications in terms of whether you should get the same inferences regarding the data set regarding the experiment. But I will tell you that there are arguments for accounting for stalking rules, and that stalking rules are actually more data that need to be taken into your model. They can be modeled by parameters. That's one counter argument for when someone says that the likelihood principle fails, basically. So to recap, likelihood principle has two versions. One of them tells you that you're going to get the same inferences using the same model if your likelihoods are proportional. You should be making the same inferences. That one's pretty okay. Should be obvious simply from sufficiency, what we've done with sufficiency. Another one tells you that you should be getting the same inferences, or you should be making the same inferences, even if you're using different models, which doesn't really seem to hold in all cases, particularly cases where there is a stalking rule for generating the data. So there are a lot of thought camps on this, and some of them argue that the likelihood principle will work. It's just that you're just framing the problem incorrectly. Again, some of them argue that it depends on the method of inference that you're using, and that is why this is considered somewhat of a contentious topic. But yes, so this is the likelihood principle. Any questions? No questions at all? No, I guess. Yeah.
So from the beginning of the stage, do we have the sense, are the x vector and y vector from the same population?
So yeah, that's what I was saying. So they don't have. So there are two ways to think about this. If they are from the same distribution, I'm assuming that's what you mean when you say they are from the same population. If they are from the same distribution, then the likelihood principle is going to hold regardless. It just follows. So in your book in Salem and Berger, there's a theorem called Birnbaum's theorem. This basically tells you that you have two conditions for the likelihood principle to hold. One is sufficiency if you're using sufficient statistics and they're equal. Sufficient statistics for y and x are equal. And the second condition is the conditionality principle. So I'm not going to go too much into the conditionality principle, but basically it is the source of the whole statement of your inferences should depend only on the observed data. Basically, it's saying that if you only observe x, then your inferences will depend on x. If you only observe y, your inferences will only depend on y. That is what it's saying. So, again, the point of argument is that if they're from different models, does the likelihood principle follow naturally from these two conditions of sufficiency and conditionality? Sometimes it does, sometimes it doesn't, depending on the two models. It will always follow if they're from the same model. Any other questions on this? No? Yes, I will be posting the slides. So, yeah, since we missed a bunch, I think the only thing that we really missed is basically some references. Obviously, your textbook that's included in the references. There's a whole book on the likelihood principle by James Berger. It's a pretty interesting read. And there's the proof of the likelihood principle. It's outlined in Casella and Berger. Basically, that's Birnbaum's theorem. That's the proof for the likelihood. There were some issues with this proof. So some people did improve on Birnbaum's proof. And I'm linking a bunch of these articles here. And this last one is Debrameo's criticism of the likelihood principle. Again, this is a criticism of the strong likelihood principle when you have two different models. And basically the argument is no, the likelihood principle should not naturally flow from the two accepted principles of sufficiency and conditionality. So again, that's the major point of argument. You have sufficiency, you have conditionality. Statisticians agree on that. They don't really agree that the likelihood principle always flows or follows naturally from these two. Yeah, so yes, I will be posting the slides on Slack. And if you guys don't have any questions, then I guess that's it for the likelihood principle. I will be here, obviously, until the end of lecture time in case someone would like to ask something about this.
So where would you see this, or how would you use it in an application?
Yeah, I was actually hoping to avoid that question.
Yeah, I'll take it back. It's fine.
Excuse me?
I take it back. It's fine.
It's fine, it's fine. So yeah, I just didn't want to disappoint you. But yes, you will probably not use this in application. It is just an argument that has to do with theory and foundations of the schools of thought. Let me just tell you one nice example for this. One place where it's relevant. Suppose you're doing clinical trials, for example. Let's say you have the issue of when you're doing clinical trials, there's issues with ethics. Do you want to give people something that you know doesn't work? Or if you know that something works, do you want to keep giving people the placebo, for example? Versus the fact that you also decide to maintain your ethical obligations, you also want to get as large of a sample size as possible. You want to keep running clinical trials, you want to keep getting better results or more accurate results, to use a better word. And the likelihood principle says that if you decide to stop maybe at 50% of your planned trial, let's say this is your first data set X, and you get the likelihood, and so if you then continue on until you get the full data set, 100% of the data set, then the likelihoods should be proportional up to a constant. And in that case, you don't really need to adjust your inferences. So the inferences you're getting will be the same according to the likelihood principle. But again, there's the issue of the stopping rule here. If you're doing a different kind of inference, let's say just the typical hypothesis testing, you probably want to adjust for the fact that you're testing multiple times. So if I stop at 50% and then do a hypothesis test and then I do another one at 100%, I need to adjust for that. You need to adjust your error rates. You wouldn't be getting the same error rates if you're testing twice. But the likelihood principle says it's okay. Some versions of the likelihood principle, because some arguments are that if you include a stopping rule, then you really need to rethink likelihood principle, or that it doesn't directly apply, that you need to take into account the stopping rule to your likelihood principle. But that's one of the application areas of argument, is that do you need to adjust your analysis in such a case? Do you need to account for the fact that you've tested twice? Or would you just go ahead and say, okay, the likelihood principle says it's okay, so I'm just going to do the same thing, I'm not going to change anything about my procedure. But yeah, so this is one example where you would want to think about the likelihood principle. But again, the issue with this is that a lot of people in the likelihood principle supporting camp say that, okay, stalking rules are data stalking rules, but in and of themselves are data that you need to account for in whatever likelihood you're constructing. So in terms of, yeah, I wouldn't say it's something that you would come across a lot, but it's an interesting argument when you think about the theories underlying statistics.